Okay, so let's discuss the what is called the asymptotically flat setting. So we have this initial data now, we have MGK, and the asymptotically flat setting, in that setting, the initial data are initial data for some space-time, for some isolated system, basically. So, of course, if you think of Minkowski space-time, you just read off if you take a constant time slice, that would be identically a Euclidean space. In the asymptotically flat setting, we want the initial data to asymptotically behave like that. We have the following definition for this. In this talk, we define it like this, although one can do it slightly broader or differently. So we have this triple MGK, so this is an initial data, and this is again, Mg is a Riemannian manifold because this should be space-like, and K is a symmetric 0-2 tensor. And it is called asymptotically flat, and here we do one end, although again you can do several, but here we do, so asymptotically flat here means that you can cut out the compact set of the initial data, and there is a diffeomorphism from the complement of that down to Rn minus a closed ball. The metric here, G, the metric on the initial data, will decay to the Euclidean metric with the following speed and in the following sense, that if we think of so we think now of the image under this diffeomorphism in Rn minus the closed ball, we think of we take Cartesian coordinates and we think of delta, the Euclidean metric, of course, can be thought of as some background metric here, and we think of G as something that we push down via this diffeomorphism. So I slightly abuse notation here, but G here is the metric that we push down via the diffeomorphism from M and down to Rn, and it has to decay to the Euclidean metric in the following sense. Now, of course, here we have Cartesian coordinates, so this is in that coordinate system. This delta is nothing but the identity matrix. But of course, we could have written this in polar coordinates as well. And we will later when we talk about hyperbolic metric. Here, this assumption is made so that the following notion is partially well defined, at least. So this is so one talks about the ADM masses on these initial data, and if the metric is asymptotically flat, and if the scalar curvature is integrable, then the following quantity is well defined as a limit. So the following quantity is nothing but the integral. Here, the limit of the integral over the spheres. I have written this now in a slightly more general form than below here, so this is when again we do this background Cartesian coordinates in the diffeomorphism. Everything here, by the way, is integrated down in the image of the diffeomorphism. So one has this one form, and one takes outward pointing unit normals, and then take the limit, and Cn here is defined to be this quantity, and this in turn is chosen so that when we take, previously we talked about Schwarzschild, and if you take a t equal constant time slice, then that will be an initial data that is asymptotically flat. It will be Riemannian, time symmetric, meaning K, this would be identically 0. And the ADM energy would equal the mass parameter. It is not a difficult thing to show that if that using Stokes' theorem, one can integrate over an annulus and take an estimate. So the scalar curvature integrability and the decays of the metric, as in the previous slide, will will ensure that this would be thought of then as the outer boundary integral of that annulus, and the limit then is well defined. So, and of course, the first question you may ask now is this even non-negative, and this is where the positive energy theorem comes in. Let me first just define for you also the AGM linear momentum. So same assumptions, and here we have this following quantity that now and this is now pi here is k minus the trace of k times g. And this is meant to be, of course, understood to be meant in the sense of components. And one can consider the ADM energy momentum vector as here below. And then one talks about the mass as the really Minkowskian length, if you will, of the, but here we have an opposite sign convention. So the negative of the Minkowskian length. Now, of course, so we come to the question of positive mass, positive energy and positive mass, where the first statement is just that the energy is non-negative, and the second statement is that the energy is bounded below by the length of the ADM linear momentum. So for this talk, we will focus mainly on the positive mass. But so let me simply mention these a few very important results. So historically, this was first proven, the positive energy theorem was first proven to be true by mathematicians Jang and Jang in '79. Well, and of course, recall that the dominant energy condition in the Riemannian setting is nothing but the scalar curvature being non-negative. So they proved it for dimension 3, and soon afterwards dimensions 4, 5, 6, and 7. And the assertion is that the AGM energy is non-negative and vanishes if and only if the initial data is isometric to Euclidean space. The latter part of this is called rigidity, and we will not go too far into this talk. And let me mention, and so this is again the Riemannian version of the positive mass theorem. If one has a non-trivial 0-2 tensor k non-zero, then then one talks about the space-time setting, and the same assumptions here. Oh, and of course we're assuming that the initial data is complete here, which is more than we stated above. Here in the space-time setting, one assumes again the dominant energy condition, and the assertion is then that the ADM energy is non-negative and vanishes if and only if we embed embed isometrically the initial data into Minkowski space with the induced second fundamental form being K. Of course, so the proof strategy in the Riemannian setting, so there are two main approaches, so there are two main approaches generally in proving positive mass theorems, and the drawbacks of both and advantages of both, of course. But the drawback of the so-called spinner method that was used by Witten in '81 was that you need to assume that the topology of the initial data is spin, and but it works in all dimensions. On the other hand, the minimal surface approach does not assume, you don't need the spin assumption for that, but the problem with that is that you can develop singularities in these dimensions above 7. So here this was proven first, and like I mentioned, in dimension 3, 4, 5, 6, and 7. But in 2017, Shane and Yao again, using minimal k-slicings, showed, and a bit more mathematics of course, but showed that this holds true in all dimensions. That is of course only the Riemannian case, and the space-time case is a bit broader, and that will be that is where the Jang reduction comes in. So here one does the following deformation. So let me say a few words about how the Jang deformation is done. We will not quite go into it yet, but let me say a few words about it. And so one forms this Riemannian product. So the idea basically is that you would like to try and deform this space-time setting down into the Riemannian setting. The Riemannian setting we take now to be proven to be true, and so one would so we form a Riemannian product M cross R, and with we simply multiply the initial data manifold with a Euclidean factor basically, and we solve a certain equation called Jang's equation. And the idea is that the graph of that equation is going to be an initial data. It won't perfectly be an initial data, but that is, we can take that as the idea here. We want to deform down to the Riemannian setting, and that we do by solving a certain equation, which is Jang's equation, which is this equation. So this is basically the statement that we think of K now as trivially extended up to M cross R. So that is to say, it acts trivially on time vectors, time derivatives, and the Jang equation or J of F equals 0 is basically the assertion that the mean curvature of the graph of Jang's of the solution to Jang's equation is equal to the trace of this trivially extended K, where the trace is taken with the induced metric on the Jang graph. And so you could, I would call this a quasi-prescribed mean curvature equation. So because the right-hand side will depend on F here. So, and just to go into those details, some details about this. This originates from Peng-Su Jang in 1978. He, however, did not solve the equation, and it was used to try and look for initial data that could be thought of as embedded hypersurfaces, space-like hypersurfaces into Minkowski space. So it was first solved by Shane and Yao, and so one would like to then again deform this initial data to some manifold that has non-negative curvature, and the mass does not decrease. And in this Riemannian product, the metric takes the following form. In the coordinates induced via the projection diffeomorphism onto the graph, the metric would take the following form. This is NF satisfies the Jang equation, but most importantly, the scalar curvature is now treatable much better, because so the main problem is that we need, first of all, the scalar curvature to be integrable, and we need the scalar curvature to be non-negative. And for a function, a graph that solves Jang's equation, one has the following identity, the so-called Shane and Yao identity. And we will see later. So first of all, a couple of observations here. One observation, two observations. That first of all, We do assume, of course, dominant energy conditions, so this term is not negative, and so the only negative contribution to this is this non-negative divergence term, but one could hope that this provides enough structure to allow for a conformal deformation. And secondly, when we solve Jang's equation later, one can estimate these terms and show that scalar curvature is integrable. But more about that in a few slides.